In mathematics, a radical is a symbol that represents the root of a number. The most common radical is the square root, denoted by the symbol. When we see the square root of 9, we're looking for the number that, when multiplied by itself, equals 9. In this case, the answer is 3, as 3 times 3 equals 9. We also encounter cube roots, fourth roots, and so on. For example, the cube root of 8 is 2 because 2 times 2 times 2 equals 8. Radicals are used extensively in various mathematical concepts including algebra, geometry, and calculus. Understanding how to simplify and manipulate radicals is crucial for solving equations, simplifying expressions, and working with advanced mathematical concepts. In our exploration of radicals, we'll focus on simplifying them and ensuring they are in their simplest form. This involves understanding certain properties and techniques that help us rewrite radicals in a more manageable and standardized way. Simplifying radicals involves expressing them in a form that meets specific criteria. A radical is considered simplified when 3 conditions are met. First, the radicand, the number under the radical sign, should not have any perfect square factors other than 1. This means it cannot be divisible by 4, 9, 16, 25 and so on, without leaving a remainder. Secondly, the radicand should not contain any fractions. We aim to have only integers or whole numbers under the radical sign. Lastly, there should be no radicals in the denominator of a fraction. If we encounter a radical in the denominator, we'll employ a technique called rationalizing the denominator to eliminate it. By adhering to these properties, we can simplify radicals and express them in a standardized form that is widely accepted and understood in mathematics. When we encounter radicals with fractions, our goal is to simplify them so that the fraction is no longer under the radical sign. To do this, we can utilize the property that the square root of a fraction is equal to the square root of the numerator divided by the square root of the denominator. For instance, if we have the square root of 9/4, we can rewrite this as the square root of 9 divided by the square root of 4. Then we simplify each radical separately. The square root of 9 is 3, and the square root of 4 is 2, resulting in the simplified form of 3/2. It's important to note that if the denominator is not a perfect square, we may need to rationalize the denominator after simplifying the radical. This ensures that our final answer follows the rule of having no radicals in the denominator. Section 4. Rationalizing the denominator, a necessary step. Rationalizing the denominator is a technique used to eliminate radicals from the denominator of a fraction. This process is necessary because having a radical in the denominator is considered improper form in mathematics. It's similar to simplifying a fraction to its lowest terms. It presents the expression in a more standardized and widely accepted way. To rationalize the denominator, we multiply both the numerator and denominator of the fraction by the radical we want to eliminate. For example, if we have 1 over the square root of 2, we would multiply both the numerator and denominator by the square root of 2. This gives us 1 times the square root of 2 over the square root of 2 times the square root of 2, which simplifies to the square root of 2 over 2. By rationalizing the denominator, we've expressed the fraction in a more simplified and standardized form, adhering to mathematical conventions. Section 5. Multiplication with radicals, monomials, and binomials. When multiplying expressions involving radicals, we can apply the distributive property, just like we do with variables. The distributive property states that multiplying a sum by a number is the same as multiplying each addend by the number and then adding the products. For example, to multiply a monomial by a binomial, such as a times the quantity b plus c, we distribute the a to both terms inside the parentheses, a times b plus a times c, resulting in a plus ac. Similarly, when multiplying binomials, we apply the distributive property twice. We distribute the first term of the first binomial to both terms of the second binomial, and then distribute the second term of the first binomial to both terms of the second binomial. For instance, the quantity ai plus b times the quantity c plus d would be expanded as a times c plus a times d plus b times c plus b times d, which simplifies to ac plus add plus bc plus bd. Understanding the distributive property is crucial for expanding and simplifying expressions involving radicals, especially when dealing with more complex expressions.